Hi everyone. So today we're going to look at the first section of astrophysics, which just focuses on distances and the immense distances that we're dealing with in this section. So what we're going to do is we're going to define some units that will enable us to conceptualize and handle some of these distances. And then we're going to look at the first method for measuring these distances. Now, this diagram gives you a range of some of the issues that you have to deal with in this topic. We are at the minimum looking at distances which are for objects that we can see from the Earth, right? So that constitutes our all the planets and the closest stars which are visible even to the naked eye. Secondly, we have to consider stars that we need to look at using different mechanisms. So we might have stars which are not visible using, for example, our current situation using visible light, and we need to use telescopes, be these optical telescopes using lenses or microwave or other electromagnetic radiation-based telescopes. That leaves us to the edge of what we call our visible universe. Within this range, we can look at stars, we can look at galaxies, not just our galaxy, but also nearby galaxies, and we can look at galaxy clusters. Eventually, we will get to a point where we start talking about cosmology, where we start considering the distances not just in our visible universe, but actually the distances involved in the universe in its entirety, whatever that means. And that's something we're going to be looking at as well. We're going to be looking at what the universe actually is and what its destiny and its individual destiny will be. Things get a little bit interesting, I think, at that stage. Okay, so what we're going to look at first is just some basic issues of distance measurement using something called parallax. Now, the three main units that are used for distance are the light year. Right, now this is an interesting one. It's defined as the distance traveled by light in a vacuum in 1 year. So if you imagine yourself sitting on a photon of light, you are traveling at 3 times 10 to the 8 approximately, and you keep traveling at that speed for 365.25 days. Then that would be the distance you cover. That would be a light year, which is equivalent to 9.46 times 10 to the 15. Now this value is in the data booklet, and so therefore you'll always have access to it. But it's just important to conceptualize just how that number is arrived at. The astronomical unit, 1 AU, is a little bit easier to consider because it's just the average distance between the Earth and the Sun. It's actually quite a small distance in comparison. But that distance is 1.5 times 10 to the 11 meters. Okay, so the third basic distance is equivalent to 3.26 light years. So 3.26 times 9.46 times 10 to the 15. Now 1 parsec, and we'll be looking at its definition a little bit later, but the parsec is the preferred unit of measurement in astronomy because it's related to something called a parallax angle. Okay, and it's the way that we measure nearby stars and how far they are, right? So parsec is very much related to measuring distances to stars. Now, the definition of a parsec in terms of the angle is equivalent to 1 arc second. So we can express the parsec in meters, but we can also express it in terms of an angle. Now that won't make much sense right now, but it will in a minute. Now, what is parallax? Parallax we've come across before when we were looking at measuring from different perspectives, right? So measuring the water in a measuring cylinder and how that could lead to a systematic error or a random error. So parallax is an effect caused by changing the position of an observer. You're going a bit mad probably looking at this image continuously. But this is an example of parallax effect, of a parallax effect. You are changing your observing position and using this building as a frame of reference. You can probably see that this looks like it's standing still, but the position of the moon is changing, right? Now, the reason why the position of the moon is changing is because the observer is changing position, right? It's moving backwards and forwards. A parallax effect could be used, or a parallax calculation could be used to measure the distance between the observer and this building, which is standing still. And how would you do that? You would look at where the moon, or the position of the moon, is changing to. You would look at this displacement, right, as a way of measuring what the distance from the building to the observer is. For those of you who like playing with apps and possibly even have an interest in photography, you can create your own parallax effects by having a number of different images taken, or photos, sorry, taken from different positions, which enable you to create this kind of 3D effect. These astronomical pictures have been taken, or have been developed, sorry, by taking pictures from telescopes, from satellite telescopes, from different locations, allowing a 3-dimensional image to be constructed. But again, it's another example of this kind of parallax effect. The parallax phenomena in calculation is all about distances, and it's also about angles. The angles involved are absolutely tiny, and so therefore we need to define some angles, or angle measurement units, which will enable us to look at this kind of scale. We're going to use arc minutes and arc seconds. 1 arc minute is 1 degree divided by 60, and 1 arc second is 1 degree divided by 60 times 60. So what we're looking at here are tiny fractions of a degree based on the 60-second breakdown of the clock. So the arc minute would make sense, would be 1 over 60, and the arc second would be 1 divided by 3,600. If you're using radians, which is also very important, we use the same premise. 1 arc second in radians would be exactly the same as degrees, but you would factor in the radian conversion by dividing pi 180. So if you needed to express something in terms of arc minutes, you treat them like degrees, and then you just convert them into radians using pi over 180. So this is a diagram of our parallax effect. We're trying to find the distance from our viewpoint to the object. The parallax effect can be visible in a distant, or an object that's in the distant background, by changing your position from 1, or A, to B. The apparent position of the object changes from here to here, and you can see that effect here in the photo. This is exactly the same thing, but seen in terms of a stellar representation. How are we changing our position? We are changing our position around the sun. So as the Earth moves around the sun, if you can imagine yourself sitting on the Earth, looking at a distant star, let's see that little red point there, that's your star, right? You start, say, for example, in September. You look at where the star's position is. The Earth then rotates around the sun, and 6 months later, what you have is a completely different perspective on things. So this would be, let's have a look. So if this is in September, this would then be in February, 6 months later. You've changed your position from one extreme of the orbit to the other extreme of the orbit. What happens as a consequence? The position of the star changes from one to the other. If you're not sure about it, I suggest you try this little exercise with your fingers. Close one eye, hold your finger out in front of you, and look at an object which is behind the finger, right? Close one eye, look at your thumb, look at the position of the other object. Then, without moving your hand, close the other eye and have a look at where that object is. It should have moved. If not, you probably have something, a problem to worry about, but you definitely should see a change there, right? That's the parallax effect. The difference is that instead of your eyes, the distance between your eyes, you have to swap that to the distance from the Earth to the Sun, which would be, I guess, in the middle of your forehead, and then to the other eye. Now, this is a representation of how we then use all these ideas to find distance D, right? Which is the position from the Sun, we could say this midpoint, to this star we're looking at. Now, you might argue, hang on a minute, aren't I interested in the distance from the Earth to the star? Well, we get a lot of this in astrophysics. Because this distance is huge and this one is very small in comparison, the actual difference between this hypotenuse and this opposite side is very, very small. So they are almost equivalent. So how do we use this idea? You start in January here. You point your telescope up to here. And then 6 months later, use that same telescope and you look at that star again, right? Okay. Your telescope will be set to give you this parallax angle. So these angles will be provided to you by your measuring instrument. Okay, there's a whole field of physics associated with how that happens, and you don't need to worry about that now, right? But basically, you get that angle. Once you know that angle, what you can use is some really basic trigonometry. You know that the tangent of the angle, that angle, right, is going to be equal to d over this distance, which is between the Earth and the Sun. What is this distance? Well, we've already defined that as 1 astronomical unit, 1 AU. So we know this distance. Once you know that small d, this distance here, divided by this distance, is going to be equal to tan of this angle, which you have, right, then you can easily calculate d. Okay? Now, the tan of this angle, because this angle is so ridiculously small, right, the tan of the angle, if you look over here, there's an approximation, is going to be equal to the angle. So in the end, your d over 1 AU is equal to the angle. Okay, so that's how you would use a parallax angle. Your parallax angle is given to you by your telescope or your measuring instrument. Your AU, your astronomical unit, is a constant that you're given, right? And d can therefore be calculated. Okay, now what is the parsec? The parsec we'll define in a moment, but basically comes from this idea. The parsec is the distance to the star if the angle that you've measured here, if this parallax angle is equal to 1 arc second. Now 1 arc second is 1 degree divided into 3,600. Okay, so there we go. If this is 1 arc second, we know what 1 AU is. This distance will always be 1 parsec. I'd like you to supplement this video with this one, which is on the presentation. He goes through it very, very slowly with you as well, using a slightly different perspective, but he does make reference to how the angle's measured, so it is worth watching. Once you've done that, try the questions in the assignment, and I'll give you some follow-up over the next couple of lessons.